Vehicle dynamics refers to the dynamics of vehicles, here assumed to be ground vehicles. Vehicle dynamics is a part of engineering primarily based on classical mechanics. This article applies primarily to automobiles. For single-track vehicles, specifically the two-wheeled variety, see bicycle and motorcycle dynamics. For aircraft, see aerodynamics. For watercraft, see hydrodynamics. Components, attributes or aspects of vehicle dynamics include automobile layout, electronic stability control, steering, suspension, traction control system, aerodynamic specific. Some attributes or aspects of vehicle dynamics are purely aerodynamic. These include automobile drag coefficient, automotive aerodynamics, center of pressure, downforce, ground effect in cars, geometry specific. Some attributes or aspects of vehicle dynamics are purely geometric. These include Ackermann steering geometry, axle track, camber angle, caster angle, ride height, roll center, scrub radius, steering ratio, toe, wheelbase, mass specific. Some attributes or aspects of vehicle dynamics are purely due to mass and its distribution. These include center of mass, moment of inertia, roll moment, sprung mass, unsprung mass, weight distribution, motion specific. Some attributes or aspects of vehicle dynamics are purely dynamic. These include body flex, body roll, bump steer, directional stability, critical speed, noise, vibration, and harshness, pitch, ride quality, roll, speed wobble, understeer, oversteer, lift-off oversteer, and fish tailing, weight transfer and load transfer. Yaw, tire specific. Some attributes or aspects of vehicle dynamics can be attributed directly to the tires. These include camber thrust, circle of forces, contact patch, cornering force, ground pressure, Pledger's magic formula, pneumatic trail, radial force variation, relaxation length, rolling resistance, self-aligning torque, slip angle, slip, steering ratio, tire load sensitivity, roadway specific. Some attributes or aspects of vehicle dynamics can be attributed directly to the roads on which they travel. These include bank turn, cross slope, drainage gradient, and cant or super elevation, road slipperiness and split friction, surface roughness, International Roughness Index, profilograph, texture, driving techniques which relate to, or improve the stability of vehicle dynamics include, cadence braking, threshold braking, double declutching, drifting, handbrake turn, heel and toe, left foot braking, opposite lock, Scandinavian flick, ski, wheelie, analysis and simulation. The dynamic behavior of vehicles can be analyzed in several different ways. This can be as straightforward as a simple spring mass system, through a 3-degree of freedom bicycle model, to a large degree of complexity using a multibody systems simulation package such as MSc Adams or Modelica. As computers have gotten faster, and software user interfaces have improved, commercial packages such as CarSim have become widely used in industry for rapidly evaluating hundreds of test conditions much faster than real-time. Vehicle models are often simulated with advanced controller designs provided as software-in-the-loop with controller-designed software such as Simulink, or with physical hardware in the loop. Vehicle motions are largely due to the shear forces generated between the tires and road, and therefore the tire model is an essential part of the math model. The tire model must produce realistic shear forces during braking, acceleration, cornering, and combinations, on a range of surface conditions. Many models are in use. Most are semi-empirical, such as the Pledger Magic Formula model. Racing car games or simulators are also a form of vehicle dynamics simulation. In early versions many simplifications were necessary in order to get real-time performance with reasonable graphics. However, improvements in computer speed have combined with interest in realistic physics, leading to driving simulators that are used for vehicle engineering using detailed models such as CarSim. It is important that the models should agree with real-world test results, hence many of the following tests are correlated against results from instrumented test vehicles. Techniques include linear range constant radius understeer, fishhook, frequency response, lane change, moose test, sinusoidal steering, skid pad, swept path analysis. See also, automotive suspension design, hunting oscillation, important publications in vehicle dynamics, multi-axis shaker table, vehicular metrics, 4-poster, 7-post shaker, references. External links. 1. An open resource and wiki for information on the vehicle dynamics of racing cars. Further reading. Egbert, Bakker. Nieborg, Lars. Pledger, Hans B. Tire Modeling for Use in Vehicle Dynamics Studies. Society of Automotive Engineers. A new way of representing tire data obtained from measurements in pure cornering and pure braking conditions. Gillespie, Thomas D. Fundamentals of Vehicle Dynamics. Warrendale, Pennsylvania, Society of Automotive Engineers. ISBN A978-1-56091-199-9. A mathematically oriented derivation of standard vehicle dynamics equations, and definitions of standard terms. Millikan, William F. Chassis Designer. Euro Principles and Analysis. Society of Automotive Engineers of Vehicle Dynamics as developed by Maurice Olley from the 1930s onwards. First comprehensive analytical synthesis of vehicle dynamics. Millikan, William F. Douglas L. Racecar Vehicle Dynamics. Warrendale, Pennsylvania, Society of Automotive Engineers. ISBN A978-1-56091-526-3. A latest and greatest, also the standard reference for automotive suspension engineers. Limited. JAR paragraph RNSEN Reimpel. Helmut Stoll. JAR 1/4 GENW Betzer. SCRIBD.com. The Automotive Chassis Engineering Principles. Translated from the German by AGET. Warrendale, Pennsylvania, Society of Automotive Engineers. ISBN A978-0-7680-0657-5. A Vehicle Dynamics and Chassis Design from a Race Car Perspective. Guigiani, Massimo. The Science of Vehicle Dynamics. Dordgt, Springer. ISBN A978-94-017-8532-7. A Handling, Braking, and Ride of Road and Race Cars.